Hey, it's Lane. How are you?
Okay. How about you?
I'm good, thank you. Well, happy Monday. I'm Michelle.
Hello.
Okay, so there are two of you, and it's 5 o'clock. So let's get started. So I'll go ahead and screen share here. Let me make sure my stuff is ready. All right. So today we are going to go over concurrency, which is chapter 6. And in this particular chapter, we're going to talk about two main, one library and an extension. So You can also find the assignment in Canvas. It's posted here. And then I'll add the video and we just have the lab left to do on Wednesday. Okay. So for now, what we're going to do is we're going to talk about asynchronous programming, and then we'll talk about the approaches within asynchronous programming. Then after that, we're going to talk about reactive programming, which is another way to really look at how we can incorporate some of the approach in how we can maximize the performance of our application. So in asynchronous programming, this is a form of parallel programming. And I think in some of the prior chapter, it briefly touched slightly on some of the concept with parallel programming, but we're going to get into how we're going to be able to write functions and coordinate the execution of your function in a program in that it's not going to hold up your processor for the execution. So asynchronous programming is a way that we can separate different part of the application into threads. And with the thread, we're able to coordinate the execution of our certain part of our program. It is used to improve performance and overall responsiveness of the program. You often find this in web development, and you know that Python is often used in web development for various applications. So compare that to synchronous programming. You're going to have a request and the CPU going to respond, and then you will have a second request, and then it's going to have a second response. Well, in asynchronous programming, you can have requests 1 and 2. And what you can do is you can set it up in a way where it is going to be sequential in that it will be able to respond to the first request and free up resources for the second request as well. So Python has a library that's called Asyncio, but we are going to look into some of the sub area of your asynchronous programming. So an example that the book provided and the documentation provided is that it's instead of waiting for each of the requests to complete, and it's going to go from the first to the second, then what we can do is we can use what's known as the coroutines to be able to submit the second request while the first request is being fulfilled. And so we would have it in queue. And you see this with a lot of the software that we're using. If you're playing a game online, you see that, especially in networking and communication, you also see a lot of the example being relayed in this particular chapter. So what we can do is we can get the second request in queue while we're responding to the first request. And so that way it's going to free up some resources for us. So what I did with your notes is I took some part that would be from the web, and I took some part from the book. While the book uses, the same example throughout, it does provide their own approach. So we wanted to take a look at some of the documentation that's provided that would be parallel with Asyncio, and also we want to also look at what the book is giving you. So the models that what you see comparing the asynchronous model to synchronous model, when you have a synchronous model, it's very linear, where that it's, let's say that you have 3 functions, it's going to execute the first function based on its call, and then the second function when we call it, and the third function when we call it. And so your timeline for that is going to be just linear, going across or from top down to the bottom of your application or your code. Now, in a threaded model, what we can do is we can separate each of the tasks into separate threads. And what we can do is we can use the group of threads to be able to execute separately. And this is what you see as a functionality of our modern processor, is that it's able to multitask. And in this chapter, it really addressed how you can write an application that will be multitasking. So it's able to handle and execute multiple tasks at the same time. So when you're using threaded model, you would see that they are separate units and it's addressed as individual units. Um, in that sense, you do have some time saving or performance improvement there. In the asynchronous model, what we can see is that task one is shown in green. And what it will do is it will get task one loaded, then it's going to take task two and put it in queue, then execute task one, then queue task three, execute task two, and queue the next task. So because we have multi core processors, we're able to implement these things all at once, utilizing the existing resources in our system. So for programming, we look at the type of input and output devices that would be implemented for memory. And if you are familiar with assembly, assembly is programming language that's used at the low level, where we would work directly with the machine instructions to be able to execute a certain task called subroutine. So in that sense, at the low level, what you have is you would use a storage location that's known as registers. And registers exist inside your processor. So your processor would have these storage space and it would have different type of registers. And so in order to execute certain tasks, it would then use the register to store certain value or instructions that needs to be executed. And in ultimately all the things we've used, it's going to come down to calculations of the binary values, right? So depending on the architecture on how instructions are different, but ultimately all instructions in all assembly language really breaks it down to what we see in arithmetic operations. That's what the computer was designed to do in the first place, and we continue to use it, but we elevate it using the arithmetic operations in a higher sense, where we can apply it for different things like videos, streaming, internet connection, and so on. But ultimately, your computer breaks everything down into binary and calculate it as a value, and it only adds. So at the low level, what you see is registers is being used, and it's within the processor. Then you have cache, and cache storage is quite common all throughout different applications, right? I just talked to my networking class last week about cache, how cache is used to be able to store information about IP addresses and MAC addresses. So the computer would use cache as a storage, and it could be inside or outside the housing of the processor physically. So you have level one, level two, and level three cache, and all of these are sequentially existed. So level one cache would then be inside the housing of the processor. And in order to have level two, you have to have level one. So each of the level cache is built on one another. It is slower than registers. It's used for frequently store operations and instructions. So that way it doesn't have to repeat itself in the computation. It just refer to that location to continue to execute. So if you have a function that require a specific element that would that would have some form of repetition, it would just go to that stored location, and it will be able to use the same set of instructions to repeatedly execute that instead of going back. And that with that we would save time. Then we have your RAM, which is your random access memory, and you know that all application uses RAM storage and storage within processor. Now, RAM is going to be slower compared to cache and register, and it's used to store more data. So when we're looking at larger sets of data, data that would be required for computation to execute that task, then it would go to RAM and be able to fetch it. Then we have another location called storage, and storage would then be treated as hard disk or could be solid state drive, but still it's just disk storage. So that will be slower than RAM, and then it would have the slowest transfer rate, but we would use something less, less pertinent in the storage area. So when you design your program, you have to keep in mind where your data actually physically exists. And so if we do a function call, likely that you would access all of these resources within the processor itself. So it's going to need to load it. But there are specific areas of your storage that your system would refer to in order to access certain type of data that has been stored. So those are the 4 primary locations. Now let's switch back to the assignment. In the first question, it asks you to define asynchronous programming and describe its purpose. So we can say that it is a form of parallel programming in which a unit of work is allowed to run separately from the primary application thread. And when the work is completed, it notifies the main thread about the completion or the failure of the work or thread. So what it does is it's going to communicate with the main thread, and it's saying that it's completed. So whatever is in queue, it's able to load that and execute the next in queue. And when you're looking at your task manager on your Windows, or when you're looking at your system when it's running processes, a lot of this is integrated into your operating system to be able to work with your multi-core processors. So that way we can handle multitasking activities that the user would demand. For example, like using the browser while on Zoom, or be able to chat while you're watching a video at the same time. So all of this really is designed to improve the application performance, because if we wait for each of the tasks to be completed, then our system is going to be extremely slow, in that it has to wait for the resources to free up in order to keep that resource for the next task. We don't want that to happen, so we want to really think about how we design the application so it will be able to handle different tasks at once. And the second part about the purpose is that it is widely used to build responsive services, especially if you're looking at web-based services, and also user interfaces, because the user are going to wait and for the response from that particular task. So if I'm using an application that's web-based, I'm interacting with it, I want to make sure that I can quickly use it. Otherwise, the wait time, if it's too long, then it becomes irrelevant. So in that sense, when you think about Python in application development, you have to think about how responsive you want your program to be, what kind of performance level that you're striving for, what type of resources that you have, right? And then whether you should have some kind of interaction or interface. And we'll talk about reactive programming later on. Okay, so those are the things that I've noted in your notes document, and you can simply clip that from there, or you can retype it if you like. Now, we mentioned that we have 4 locations for type of memory in which the CPU can utilize for system operations. And those are registers, cache, RAM, and storage. And we can say disk storage, but on the newer storage type, they are SSD, solid state. They're no longer spinning disk. And it asks you, why should a programmer manage I/O device resources? This is important because the resources should say from, I have a typo. From IO devices must be handled to prevent CPU waiting aimlessly for the IO devices to operate the task. So if we have to wait for the disk to, to free up the space in order to execute the next task, that might take a long time. As we know that all of these devices are handling data transfer at different rates. So you have RAM that's going to be accommodated by the bus or the socket where it's connected to. Then you have the processor. It would also have its own socket, but then it would use one clock cycle in order to execute one instruction. So then if you have to wait for a task that would require many clock cycle, then that would take a long time for your application to complete. So then we would think about how the tasks are being operated and where is the location where the instructions and the data for that task is stored. Okay, so before we answer number 3, do you have any question for number 1 and 2? Now, when you look at the content of this chapter in the notes, right, you have to think about the abstract level, how we're able to write the statements and design our program to really divide up, right, things that would be time or, certain wait time in that we would handle certain things while we would submit or load the second request or the second task. Okay. Then after the section on IO and memory, we would go into how does Python do multiple things at once? And there are different approaches in this. So overall, when you look at this, you would think about multi-processes. CPU processes are shared and it's supported by spawning multiple processes. In that way, it would execute simultaneously. But how does it do that? How does a developer make the application do that, right? We're going to get a little deeper into how we would design it. So we can create multiple processes. And then you have the second approach, which is multi-threads. And so a thread simply is a line of execution. You can have many different threads and multiple threads in the context that they are sharing access to the common resources. So I can have many threads that's going to revert to, right, the registers that's going to be storing the instructions and the data for the execution. Now, it would be very difficult to really write it at that level as we are learning higher programming language. So we want to really refer to the operating system to handle the thread grouping and able to handle the thread in the execution. So for the global interpreter lock, the GIL allows only one thread to run the Python code at any given time, even when you have multiple threads running the code. So when you use CPython, when you compile the program, GIL prevents multiple core concurrency as though you're running a single core. So that really defeats the purpose of having multiple core in a processor. So if we're relying on the thread approach, even if we're using multiple thread at the low level, at the global interpreter lock level, you would see that it's only able to handle one thread at a time. So then in Python, what we can implement is what's known as coroutines. And there's another section in the notes that talks about coroutines. So coroutines are generalization of subroutine. And think about subroutine as a function at the low level, right? So when I teach assembly, I talk to my student about, writing the subroutine, which is a function at the machine instruction level. So then in that sense, what we can do is we can use cooperative multitasking in that the process will give away the control periodically. So it's truly really sharing the resources in that at some point in time, it's going to release that resource for other activities. Okay. So then in Python, what we can do is we can implement a library and we can use what's called a yield statement to be able to control the resources in a certain period or when it's idling for our application to run simultaneously. And we're going to come back to this approach. Now, asynchronous programming, as we mentioned earlier, that it's still going to take one execution step at a time. And the system may not wait for the execution step to complete before moving to the next one. So it's like you are managing the first task and then put the second task into queue, working on the second task, and then coming back to the first task, and it's going to keep switching back and forth or going to the third task and so on. Now, this really means that the program knows what to do when the previous task does finish running. So then it's going to go to what's in queue. Okay. So we're able to save some time by queuing the subsequent task. We're just submitting it. It doesn't execute until the first task is complete. So in a way, it is still sequential, but we're able to utilize the second, the third, or the fourth core to handle the queue for all the other tasks while the first task is being completed. Okay, so we maximize the resources at that point. Now, concurrency allows multiple jobs to take turn accessing the same resources. So it will free up the resources for the other requests, like disk, communication, okay, or processor in some sense. So the goal of concurrency is to really prevent the task from hoarding and blocking all the resources for the subsequent task. Because if you run things linear level, right, one at a time, if you have, let's say, 100 tasks, and if your first task is hanging, right, it never completes, then all the subsequent tasks will never be accomplished. So we have to implement concurrency so that way we would see that our application would be faster by setting up the other task. So then what would happen is it's going to split the task into the smaller units. And then it's going to execute it out of order. Okay, so it's going to load it into portion of that task. So the first task is being worked on, then all the other tasks is going to break that down into smaller tasks, and then it's going to prepare those subtasks, right, for execution. But then when it executes, it's going to be out of order. Okay. So the example that we see here is that when we submit network requests, okay, we would launch the request, wait for it to finish, and then launch another one and so on. But if you're familiar with packets and routing, what you see is our systems, right, break the packets, your data into pieces, okay? And it's going to receive the data as it goes. And then when it for TCP, it comes back and we rearrange everything. But if you're using something like UDP, when you're submitting a network request or you're watching a YouTube video, right? Your data doesn't come back sequentially and in order. It's going to come back. So your system is going to process that piece of data that could be later in the packets and be able to put that together at some point. Okay. So when you implement something like this, or think about an example like this, you would see that concurrent approach is a way that we can address everybody at once. So let's think about it this way. A person have many children, right? And all the kids are asking for different things at the same time. So that person is like the processor. So if we're able to, divert our attention to all the children and be able to keep them somewhat satisfied from, partial um, partial response, then we should be handling all of the requests at the same time. So that's really an approach in concurrency. Okay. All right. Now, this is an example of how you would define a function, such as network requests. And so here, what they did is they implemented a time wait, which is 1 second. And what it's going to do is it's going to calculate the number using that function. But while it's waiting for that 1 second, right, you can free the resource up and be able to allow the processor to handle the other task. Okay. All right. So in the next question, it asks you to describe how the coroutines are used for cooperative multitasking. Coroutines are generalized subroutines. They're used for cooperative multitasking where the process voluntarily yield or give away control periodically. When idle, to enable multiple applications to be run simultaneously. And the majority of the content for this assignment is to really talk about the concept and writing down, the purpose, right, of these concepts, because before we can dive into it, we have to really understand what each area does. And for number 4, it asks you explain the primary goal of concurrency in development. So its goal is really to prevent tasks from blocking each other by switching among them when one is forced to wait on an external resource. So if we purposely program in a wait time, we can then free up the resource so that way we can handle the other task. And that is what is shown in the example. Any question? Okay, so next we are going to get a little bit deeper in concurrency. So here provides you with the example, and what they used was they used, right, the wait for the network request. So before it can crank out, so it waits here and it's going to return and it's going to calculate the square. And then it's going to come back, it's going to call on the network request. Okay. So with that, we're able to handle multiple functions at the same time. Okay. So in the example that they would do a fetch squared 1, 2, 3, 4, right? And the result, you would see that it would just, when it calls that function and we pass the value in the parameter, right, it's still going to crank out the result for us. But what happens in the back is that what we're going to do is we are going to submit the request in the orange, while the blue is having wait time. So whenever that the first fetch, let's say it's going to submit, the other one is waited. Okay, I'm sorry, the first one is waited, the second one is submitted. Then we would see how we would be able to spend the time. So we're still going to be able to produce the same result. It's just we're able to save some time in that we would free up the resources for the machine instead of it just sitting there waiting. So multiple functions or coroutines are combined contiguous registers. Yes, but so in the low level, what happens is before it goes into, it calls on the subroutine, there is a register that's used. Think of it like a temporary register where it needs to be able to load it. And so the processor would go to that register, that specific register, to see what's in queue. So what happens is when you set that wait time, it's going to go to the IR, and then it's going to look at, right, what needs to be loaded, and then it's going to bring that in to set up. And it's only setting up, it hasn't execute yet. Then after that 1 second is done, then it's going to execute the first task. Then since it's already loaded, right, then it's going to execute the second task. So there are dedicated registers, like there are registers that we store data in, and then there are registers that we store specific instructions or instructions that is moved from one area to another, in that it's going to use that for the subroutine. Like go to in C++. Sort of, but go to, yeah, it's kind of like a jump. But when you do a jump, it's going to go to a certain location, but the jump can go to a label. And C++, the way they use it is like a label process. So in the back, that label is actually in the data registers, and then but the instruction itself needs to associate to that data register. So it needs to bring in the instructions, and then it's going to use the address of the data to with the instructions, and that's how it's able to submit it. Yeah, C and C++ have some similarity at the low level. Okay. Other questions? So think about concurrency is a way that we can prepare, right, the next function call while we're executing the current call. And that's what it is. Okay. And so it is, we need to really think about how we section our code, what we need to implement as statements in order to really handle a lot of that. So if you are able to design that, you don't have to force, right? You're not operating in a linear structure, then you can think about how your system, your application will be managed much faster. Okay. So callbacks are a call that's responsible for waiting, right? Like you saw the time sleep. So we can implement a pause basically to the first function by doing a time wait. Okay. So the example, so while that's happening, we can work on the other tasks as we would prepare them for the calls, right? That's what you see illustrated in the picture. So then in the example here, what you see is simply we have a function, it's going to print out our message, right? And in it, we just add that wait time, that 1 second. So in that, your processor would then go and be able to submit for the next function call. So the callback is a function will be called when the wait time expires. So when this 1 second is up, right? That's going to be a function that's called after it expires. That means it's going to go and load the print. Okay. So it's going to execute the print there. Now the beginning example, what you see here is they're using threading. Okay. And then in the later example, you would see that they implement the Python library. So keep in mind that we're using threading here. Okay. So then they use the example as the defining the callback function here, right? And so we can do a countdown, and as that time expires, it's gonna call the function that will be the callback. And so as you can see, that happens in that we intend for these functions to be placed a certain way in a different sequence of time. So that way they're not sequentially waiting, right? But we are purposely put certain things into pause while we're handling the others. Now, the one on the bottom there is a synchronous, right, type of approach. So when you call this function, right, and pass the parameter, it's going to run the function. When it finished, it's going to run this one and it's going to run that one. Where in the other one, when it paused, it's going to execute, right? It's going to load the second task, it's going to execute that, and it's going to come back. So it's going to do a callback where it's going to revert back to the first task. And so when you think about applications like compression and encryption, those require a lot of processing and resources, right? Storage. So in that sense, you know, it needs to really be handled with concurrency. Okay. All right. Any questions regarding callback? So in question 5, it asks you, why is callback important in concurrency programming? Because it implements the wait, which allows the rest of the program to continue execution without waiting for the beginning of the program to execute. So things like web-based, like what we said, networking, communications, cloud, right? User interaction. Maybe for mobile applications, we need to really think about how we can implement this approach. Concurrency is like foreground and background in the back. Yes, sort of, yes. So your OS does something like that too, right? If you look at your task manager, if you're monitoring your processes, you would see that, you know, all your other processes are some of the processes are queued, some of the processes are going, some of the cores are handling different processes, and then at time you would see you know, a switch in that it's going to be able to jump back and forth and be able to manage all of that at once. Okay. But the OS deal directly with thread, so you do see some thread management with the operating system design. So for 5, we already state why callback is important. And in the next section, it talks about future. So we said earlier that while the first task is working, being executed, the second one or another one would then be submitted, right? So future simply is an object that is going to store what's in queue. It's a memory location in which it could be used to keep track of all the callbacks throughout the program. And the callbacks really revert to the resources, right? That will be used for the execution. Because when we pause it, we free up that resource. So we need to find a way to really track it. Okay. So when you create futures, all that is an object. And this object is used to track callbacks through the program. Because we have to make sure that there's some kind of management capability in that we don't have any kind of conflicts, along with, you know, which resources is going to be freed up and how it's going to be used. Any question? In the future section, you can find that on page 5 going into page 6. So this is really an abstraction, right? All of these concepts is based on abstract. This is just future allows us to track the requested resources, as we said, that were waiting to become available. So it is a pattern, and that's used to track callbacks. And when we implement futures, Python has a future class, and we would use concurrent futures from the future class. So you can instantiate an object, you can construct an object, and that object is going to be in charge of tracking. So here what you see is an object name is FUT, right? So when you create this object is going to be at a certain location. Now, if we put something in the parameter for the future, like this, like the string hello. So future is never really what you would use. It would just represent the value that will become available. It's just to really set up for the future execution, hence the name, right? So it's just going to store what will be loaded into, you know, for the resources for the next execution. So here what you see is when it's set it, right? It's here, but when we have it on the next part here, then it's going to return. So once it's execute, then it's going to go and retrieve that string and give you that string. But it needs to load that it needs to submit it, right? As part of the resource. So how you can, when you use future, if you implement future, you would say from concurrent.futures import future, because this is the class that you're using, right? And this is the method that you need to have to be able to construct the object. So in this function, what we have is we would have an object from this class, right? Instantiate, you construct an object here. And then we also implement the thread. with the wait. And then we would start the time. You guys know what lambda is used for? So when you define a function that doesn't have a name, lambda is a placeholder for a function name. Okay. So here what we have is we can plug in lambda. So what that is it just allocated the storage for potential function with a certain name. We just don't have an identifier for it. Okay. So this allows you to return the future values as we return from this function, right? So beyond this, right, we would then use framework. So in the next part, we're going to talk about a framework that can be implemented in Python to handle future. Okay. So if you write it manually, you would see it like this, where you would define the function and then set up the actual content for future. So with that, it would give us the resource status, what's being canceled, what's being scheduled, what's being handled as far as exceptions. And the output is shown here is that you would see that how it would have the first call, it waits, then it does a second call, right? So future allows us to track what that would be for the first call when it goes into wait. It gives that resource for the second call. And then it's going to track it again for the resource. So the next call, the after call is going to happen, and so on. And the book gives you quite a few sections where it goes into specific example, like how you would be able to submit a call. So for the lab this week, we will be using something like this, and we can write a simple program, but we would, implement these programming approaches so that way you can see how that's done in the case that if you need it for specific purpose or goal, right? You'll be able to do it. Any question? So we talked about futures. And then another element of this would be implementing loops, event loop. So the challenging area as you finish the future section here, after you look at the example, you would see that asynchronous code is nested, and it can be challenging to really dissect and read. So what they're saying is that because we're using callbacks, what we can do is we can look at another way that we would be able to manage the resources. Okay. And the perfect example for event loops would be network connection or database query. Things that get triggered by execution of the callbacks when a certain event takes place. So if you're thinking about web server and you're connecting to the web server, right, you submit that request. Once it reaches the web server, when it receives that request, it's going to have to reply. So in that case, you would see an event that happens, right? There's a request that takes place. Then the web server is then going to reply to the client So there's another event that's going to take place. But in order to really get the browser to really load the content, all of these have to happen prior to that. Okay. So then what we can see is that these type of scenarios would do well with using event loops. And this is also referred to as overthreading, in which that it runs at the same time as another and simplify dealing with shared variables, data structures, and resources. So we would then need to implement a loop to handle that event. That's what it is in the background. So here we define a class called timer, right? And in it, we would have timeout. So we would have the members, variable, and methods. Then we also have another method in which that we would set the timer, start, and then it's going to go until timeout. So we can add in a loop, which uses a while loop. Okay. And we would say that when timer is 1 second, right? And we would have while true if timer is done, print timer is done, break. Right? We have to exit out of the while. So using this, what you can see is that it's going to prevent that block of the program, okay, the execution of the block. So the program can then be managed to, or other parts of the program can be handled while the loop is taking place. And this is known as busy waiting as well. Okay. So what you can do is you can implement something it's doing in the background, and then it's going to execute the others, right? So when that timer is done, it's going to come back and it's going to be able to execute the beginning task instead of hanging on to the resources and blocking the rest. So here they show you how you can have the callback in the while loop. Okay, because again, we use callback to track our resources. So you can add in the callback. And then if you add more timers, okay, then you would see that here we would add timer 1 and timer 2, and then we would extend this. So then after the first one is done, we want to go and remove. When there's no timer left, right? When it's equal to 0, then we exit. We need to get it to exit the while loop. Okay. So as you look at some of the example for number 7, it's asked us, how is an event loop implemented in a concurrent program for concurrency, right? So we use event loop as a poll of status. So it's used to poll the status of the event while allowing other tasks to be executed. A while loop can be implemented with the callback. So what it's doing is checking the status of all the other tasks to be executed. And it's going to look for specific event that takes place, right? Hence the name. So we can use what the book provides us as an example, which is a while loop. question. So if you think about network appliances and devices like IoT devices that needs to connect and do things at the same time, right? This will be a perfect approach for those. How does it pull per second? Depending, well, the way that the book uses it, it pull based on the timing that you set it, but you can have it pull however you want it to do. Because you know that each of the tasks require one clock cycle, depending on how fast your processor is. So if you have 5 other tasks to be executed, it's going to pull the other 5, and some tasks will be faster than the other, right? Then we would know. So I think the way that the author approached this is like they just use the 1 second span, but it's really down, the unit that you should be counting is your clock cycle. But you can set a timer on however you want it to really look for that. And when you look at like network systems, like the router, it pulls, right? And also a lot of our appliances really use the mechanism to really broadcast. So if it doesn't receive anything, because we just finished a chapter in art for my networking class. If it doesn't have the information for the art cache, it just broadcasts, it sends it to everybody. And so when the other system receives it, it's going to respond back. So in that case, what you see is it's really checking the status. So a lot of the things is, the programming approach is really relayed in our communication systems and the things that we use every day. Okay. So there we go. So it just needs to check the status. That's what it's doing. And how does it do that? It goes to the callback, right? Remember, callback stores the status. All right. So the downside of event loop in this, and there are a lot more pieces to, some of the pieces in the program example was kind of repeating. And so what I did was I just cut some of the important example and show you. So the main restriction of the event loop is the flow of the execution, that it should be managed by continuously running the loop, which never uses the blocking calls. So we can let the event loop to detect and execute callback when the resources is ready. And for operating system call, where you would use that for the thread, right? So the notification of the event is implemented through the OS call, such as select. That's actually I forgot to italicize that in Linux or in Unix. Okay. And every chapter, as you can see, that they introduce us to a different library and other tools inside the library. So Asyncio is a library that would be used for concurrent code. It is a foundation for multiple Python asynchronous frameworks. So when you have all of the elements that what we've been talking about for asynchronous programming, right? Like you implement callback, event loops, and so on. What you're building is you're building asynchronous framework. Okay. And so it is suitable for IO bound or high structured network code. When should you use Asyncio? You should use it for web server, database, connection libraries, distribution task, and setting up queues. So back end, you do see this library implementation because we need to be able to manage, right, multitasking across our systems, like our server, database server with web servers. And so it also provides high-level API, right? That's why we use the library, because there are tools that are created for us. And the APIs allow us to run Python coroutines concurrently. It can also allow us to perform network IO and IPC. It also allows us to control sub-processes. Remember, we talked about how it breaks it down to subtasks. And then also submit for task queues. So distribute tasks via queues, and then synchronize concurrent code. On the low level, you can use this to manage loops, run sub-processes, handle OS signals for OS calls, implement protocols using transports, and callback-based library for await is the keyword that we will be looking for. So the best way to really look at this is through their documentation. I provided a link here for you. You can click that. Okay. So this gives you the overall, and I took some of this from their website and I added to the notes. So you just have one place, but you can take a look. And here you can also click on specific. So if we are looking for coroutines and tasks, we just go there and it's going to give you that subsection on coroutines, what they are, how they're used, examples, and so on. Okay. If you wanted to go work on the sleeping, then you can look at how the sleep for the coroutine would work, where you would delay. Remember how we can make it wait? And if you're familiar with, I know that when I did Raspberry Pi with Python, right, in the summer, you saw that we implemented the wait for some of the things that we've done. Okay. So it's widely used on an IoT end. It's also used in communication system, as you can see. Okay. And we are going to work with the await as a keyword. Okay. Any questions? So for question 8, it asks you, what type of library can be used to implement concurrency in Python program? You can implement frameworks by using Asyncio. And for 9, it asks you to go into the documentation. You can take a look at their Hello World example. And that's what I use. And you can write an asynchronous program that displays 2 strings. So you can start out with the 2 strings, right? So coming back to the notes. So let me, before I go into the coroutines. Yep. This is the example you can use. So let's say that we want to display hello world separately, right? And so we would then first, we need to import the library. And then you would define the function, but notice that it's not any of your typical function. It comes from that library. So you have to use async for asynchronous when you define that function. And then in the body of the function, you can have it print whichever string that you want. You don't have to make it hello, right? And here they use main, but you can define whatever name that you want for your function. Then we're going to make it pause or wait. So we're going to do await, and we are going to use the sleep method from Asyncio. Then while it waits, we are going to execute the print. Okay. So sequentially, you see hello and then world at the output when you call that method or call that function. But in the back, you know that while it's waiting for that 1 second, it submits the second part, which is world. It queues that. And then it execute hello, and then it execute world for the print. Okay. So you can use that example. So here I just have this similar, right? I have import Asyncio, and then I define the function, but because it's asynchronous, you have to say async def and then your function name. You're gonna indent, and then we can print a string, and then we make it wait or sleep 1 second. Then we would then print, and then we would call that function. So on this one is the last part here. And you would test it with, right? You would be able to test it in the shell. You don't have to, if you do build the program, you got to make sure that your IDE sees that library. You already know the deal. Any question? So that's like the very basic, okay? And if you look further on their later example, you're going to see that it's going to get a little bit more complex. Now, in the documentation, if you go to the next section, it says that if you simply call the coroutine that is not scheduled, okay, like main, that's what they call it. That's the function, right? If they call that coroutine will not schedule. So the coroutine will not schedule it to be executed. So when you call that function, it's only going to show you the object main, which is at a location. So this doesn't run it. That's what it's saying. Okay, it just shows you where it is. So if you want to run it, you have to use the appropriate function for that library, which is Asyncio run. That's one way. Another option is to be able to wait until it times out, and then it's going to run it. So after the delay, so it says here that awaiting on a coroutine, following the snippet, it shows that hello, wait 1 second, and then the world is print, and then after waiting another 2 seconds. So they use await. Now the output here, what you see is, right, the time that it started, okay, and the time that it's finished is about 3 seconds. And a third way for us to really execute the function is what we can use is called create task. This allows you to run the coroutines concurrently as tasks. And so as you can see, what they define here is that you have a task and you are going to use create task. Okay. And in that you would have hello. And then for the second task, remember that we can break a function into subunit. That's what we're doing now, subtask, right? So task 2 is that it's going to have the world, the string world there. And then we are going to print. So it's going to wait for both tasks to be complete. It's going to take about 2 seconds. So we're going to do an await task 1, await task 2. Right? In a synchronous program, you just do a print hello and then a print world, right? What happens is if you don't ever get to execute the print hello, the second string doesn't appear. Now, when we do this is when we do the await task 1, task 2 gets loaded. Okay, into the register that's going to be handled, then it's going to execute. We're still going to see hello and then world, but in the back, we make certain things wait. So it takes approximately a couple seconds for it to go there. Okay. Any question? All right. So if we just call the coroutine in number 9, it's going to only output, or it's going to have basically it has the memory location for the coroutine object. Just say how do we? So how do we really execute the coroutine? We can use Asyncio run method or function. We can also set up await. So we would await on the coroutine using await statement and parameters. Sorry, I typed in a hurry there. And then the third way is to use create task in Asyncio. So those are 3 ways that we can execute the coroutine. Okay, any question? We're almost finished actually. Just a few more to go. All right, let's take a look at, and then it goes into awaitables. It gives you some details about how you can use awaitables. And basically that's just object that is used for await. So when you look at here, right, it's gonna go over here. It's gonna print 42. But because in the function it's returning 42 for the nested. So it's going to return 42 and then plug that in here. So the 3 types of awaitable objects, you have the coroutines, the tasks, and features. And we talked about features earlier, right? we just touch on the coroutines. So to define, again, to define the coroutine function, make sure we know this for the quiz and test, we would use async def keywords, and we would then give it a name. You can create coroutine object returned by the coroutine function. So whatever you define in the function, if you set it up to return, right? And that's how you saw what was returned from nested. And so awaitables just contain the object. Okay. Now tasks are pretty straightforward. Your task is going to be used to schedule coroutines concurrently. So you can simply declare the task object, and then you just use create task, okay, to set that up. And then what we can do is we can await task. So here it says that we await until it is complete. And so when you call this function main, you run it. Remember, we talked about it has to be run. So we run it. It's going to go here, right? Create the task. Then it's going to call nested. The nested is going to return this. Question. So we saw some example on how to create tasks, how to run, and how to use await. And so we are expected to do this for the lab. Okay. And I want to make the program a little bit more applicable than just printing out strings or, you know, looking at the actual wait time. So, and we are going to use not just Asyncio, we are going to use RxPipe, which is reactive extensions. Any questions before we go into reactive programming? So an example that they use in the book is going to be very similar to that. Okay, you have an object, but this they use get event loop, and then they would then implement that. You can make it run forever. Okay, so using this library, we can treat the coroutines as generators. Okay. So coroutines are another perhaps more natural way to break up the program execution into chunks. A function can cancel another function, task can cancel nested. Yes. Yes. But, you know, yes, you can do that, but at the same, I don't see the point if you do have a function canceling another, right? That's exactly what I said. So the example they show you there is just a way for you to see how a certain method from that library is used, but it's not, it shouldn't be applied that way. That was my point earlier. Okay. Because it's clear like that, it doesn't mean that it should be applied like that. Yeah. So your book does give valid example on how you can use something simple like, square and connection and things like that. So it does apply in a way where it's more realistic. Okay, so we use coroutine to really break up the execution into chunks or subtasks. Now that would allow the programmer to write the code that would resemble synchronous, but execute asynchronously, right? It's still going to give you the same result as synchronous, but we handle it with asynchronous programming tactics. So now in here, what they show you here is that you can implement coroutines as generators using yield statement. And so we have a definition called range generator. In it, we would have a while loop, okay? And it's going to yield I. So coming back to our page. Where is it? I lost it. Await primitives. Time map shielding. So as you can see, you can look at, we already talked about creating tasks. You can go further and you can take a look at all the methods that you can implement. Okay, you can also put shield. I think I gave. All right. So in here, and I try to take what's in the book and also parallel it with the documentation so you can see. We saw this example already, but in this one, it also used additional library like delay and what, right? So you would use Asyncio run function and then run the top level entry point for the main. Then you would have await coroutine. That would be here. You have a sleep. That's going to pause it. It's going to print. Then in the main function here, you have the start time, that's print. And then you would then have hello for 1 and 2. And then it's going to print finish. So the output of this is going to look like this. So when it started, it's going to do the start time. And then it's going to do hello and then world as it waits. And then it's going to finish. So a total of 3 seconds on how they time that there. Okay. Okay, so I think we touched on awaitable objects. Earlier we talked about features and how that's used with the callback. But if you tie this into a awaitable object, so future is a special level awaitable object. And this represents eventual result of the asynchronous operation that's going to come, right? It's going to be our future. So that's potentially it's going to happen. And future object awaited is that the coroutine will wait until future is resolved. So that object needs to be resolved in order for the coroutine to be completed. Now, they mention in the documentation that you will not need to create future object in the application level code. But to show you how that's done, right, we looked at how the future object was. So you would use Asyncio APIs with await in order to handle future. Okay. So in the book earlier, they show you how to use future class and all of that. That's at the low level, at thread level. We don't need that if we're using Asyncio library. You just, if you're using the API, you're just gonna use await in the functions for that. Okay. So let's talk about, okay, so there's a little section on blocking and non-blocking code. Okay. So we can put the blocking code onto a separate thread, and that will be handled by the OS. So Python uses what's called the executor interface that would be handled for separate thread. And you would use thread pool executor by importing in concurrent features module. So that's how you can program that in by importing in the library and use the thread pool executor. And this is just for additional knowledge, right? And so in the book, it also shows you how you can implement that. Now, in this example, when you run that method, it's going to return a Asyncio future instance that is awaited for another code. So the important part to note is that future will not run until the start of the loop. So it's going to wait for the start of the loop, and then we are going to be able to obtain the response. Okay. And this is the fuller example that you can see here. So in this program, you know what it's doing, right? So it's going to go look for the URL, whatever the response is, it's going to put it into a list. And so we would have it loop. And it's going to plug in, right, like google.com, facebook.com, and then store the result. So this is what you would see on how we can implement feature, right, with the executor here. And with that, we would treat it as a separate thread. Okay. Any question on this? So this is a little high level, but you want to expand your knowledge to all the capability of Python, right? How you can use it, what you can do with it. On the next part talks about reactive programming. And this is going to be to really re-emphasize concurrent systems. It's supposed to work with concurrency. it's designed to react or respond. So its goal is to be for responsive system. That's going to be immediate to the user. It should be handling different level of load. So it is scalable using elastic. It is resilient in that it doesn't fail gracefully, it says, in the case that it does. And we can really achieve modularity instead of having a single point failure. So you would have multiple modules to be able to incorporate, and it would be message driven in that the system cannot be tied to one block, but it should be events based. So as a message driven system, you would have responsive, elastic, and resilient. Sorry, I put the reference in the wrong spot there, but so the extensions for reactive is RxPy or reactive extensions for Python. And this is a group of libraries, not just one. Therefore, they're known as extensions. And it would have asynchronous and event-based libraries that would be used for Python program. And when you look at this, you're going to see the observable sequences and operators. So there are two elements in this. There's your observables or observable sequences and pipeable query operators in Python. And we implement operators to stream data. Okay. And we're able to use concurrency for data or event streams using scheduler. So this elevates what we were talking about earlier in that it's able to handle the data stream. And to install RxPy, you would have pip3 install Rx. So an example of that would be this one. So when we say data stream, a simple example would be just be strings, right? Here you have import Rx, that's the extension. And then inside the extension, you want to bring in operators as ops. You set up source, okay, and it's going to have alpha, beta, gamma, delta, and ellipse or epsilon, I'm sorry. That will be these strings. Now, these are the operators, pipe, map, filter. So how you want to be able to use this data is happening here to put them together, okay? And subscribe, and it's going to talk about subscribe is how basically that's going to when you're going to be able to execute it. So earlier we talked about yield, and why yield is important is that in concurrency, when you do a yield, right, it ties back to here in that the value that it's received or the result of that, right, that's going to be able to activate the next whatever task in that sequence. So observables, you would treat observables as iterables that provided value in the case the exception is raised in the sequence that it's complete. So earlier we saw the yield I is that when we need to yield that value. So when it sees that value, that means that it's going to check the status of, you know, that task is completed. And all of this is to really monitor, right, what is being sent or used across. So in data stream, you might have a lot of content, you might have a lot of data. So you can implement observer as an event. Okay, so let's answer the next few questions. We already know that our RxPy is going to be the type of libraries, or we would use an extension for asynchronous and event-based program. We would install it with pip reinstall Rx. For 13, the purpose of the operators is that it can be used to create, transform, filter, and group observables. So the operators, as what you saw earlier, we can have it map as a keyword, right? Filter as a keyword. We can use those operators from the extensions to create, transform, filter, group of observables. And to create observables, we would use observable dot from iterable method. That's the entire method. Because observable are iterables. Okay. And in the documentation, they refer to this as a factory method. So this is the method that you use to create observable. Like this, you would construct it. So you would have a name for your object, and then you would have, right, the method. And this is just going to give us range 4. So to receive the data from ops, we can use subscribe method, which execute that function as we pass each of the value. Okay. Sorry, it got dropped off. I should have shrunk it. So it doesn't execute until you use the subscribe method with that object. So observable pushes the stream of data, right, when it's ready. And an observable is also able to tell us when there is an error, an exception that occurs. Because remember earlier, it says that it would provide some kind of information when there's exception being handled. Okay, or where there is no more data, when it ends, when it's completed. So it's saying here that we would then register the callbacks to the observable subscribe. And if you look at the next example, okay. So in this, what you have is you have the same object, right? And here you would execute. And it's just going to print the next item. And at the complete, we would have no more data, which is from here. Okay. Now for this one, we're trying to range to a large number, like 10 million, and then we'll just have it only do 4, so 0 through 3. It's gonna, when you execute it, you would use the subscribe. Okay. So note that there are 130 operators available in RxPy, where we are not going to use them all, right? We are going to use some of the main ones, and we're going to use the factory method or the built-in methods, so you can see how that's done. Okay. So when do I see the operator here? I see it map here, filter, pipe. So here it shows you that the new operators are implemented in the function that can be directed using the pipe operator. So here you have a source.pipe. So then you would implement other operators like map and filter. So when you compose other operator, you would pipe, okay? And map and filters, you can have them grouped. So if you're looking for specific data in the data stream, you can filter it. You can look for the location of the data in the data stream, you would map it. Okay. And that I think is going to the next one. And you also have lowercase and so on. So when we deal with reactive programming, likely that you're going to have a lot of the data stream. So therefore, this was part of that piece. Okay, because we know that we would have user interactions and how user would either provide or acquire data. And in the book, the last part, it touches on hot and cold operator. Their operators, the example that they're using here is they use interval. That's going to give you the time interval in milliseconds to create an observable. And that will be considered hot, right? And then when you have observables that are out of the range of that given time, that will be cold. But the construct is about the same. You create an object and then you set up the interval of time for that observable. And then you still have to subscribe it. And when you use the take 4, it's only going to use 4 out of the 1,000. Okay. For output. And then when we set it to wait, so it says that in the sense, if we have it called, if it's lazy and it start producing value when it's requested, then those are going to be cold. Okay. Because it's then going to wait and then it's going to wait for the request. So that's considered a cold observable. So I think when we start doing the lab this week, you're going to see a little bit more relevant in how we can apply all of these. And you're presented with different library and different concept and how you can implement for your program to improve performance. And that's what we've been working on since the second week, chapter 1 of the book, right? So if you do have the text, take a look at the example. I didn't clip everything there because I'm starting to get a warning from the publisher that I can't, so I just wanted to really tie in the documentation and this so you do see some relevance from the textbook where it uses a different type of example, and then in the documentation it also gives you a different type. But ultimately you're going to see how the syntax is and certain type of method and how you can create an object, how to be able to really build the concurrency framework for your program. And that's ultimately the goal for this particular chapter. Okay, so last part was just to use observable from underscore iterable method. And that's going to allow you to create observable. And then when you want to execute it, you just use subscribe. Any question? Okay. Let me stop this so I can stop recording.